Hi, everyone. Thank you for attending the talk. And I'm Chengke from Peking University, supervised by Professor Chenren. And today I'm going to talk about a project on achieving high throughput on a Wi-Fi direct link. And our project is called SMUFF, that leverage on-device buffers to saturate the wireless link. And our system achieved nearly the practical line rate of the underlying wireless bandwidth. So this is joint work with Kaihong company and University of Southern California. So our journey begins with peer-to-peer wireless connectivity. So this technology facilitates data sharing between different devices and increases productivity for mobile users. So with this technology, users can easily share any digital files with others, including document, pictures, or videos. So it also allows us to transfer data between different types of devices, such as smartphone, tablet, and the smart televisions. So at the first place, why do we need peer-to-peer connectivity? So without it, if we want to share data between two devices without wire, so we require an access point and connect to the internet and use the cloud service to transfer the files. So peer-to-peer connectivity addresses this with three primary benefits. First is convenience. Peer-to-peer connection works without a central server on an access point. And the second reason is bandwidth, and it required no backhaul to related traffic and is not affected by the network congestion. And finally, it protects privacy and avoids the risk of data leakage associated with the cloud storage. And today, a growing number of smartphone manufacturers are introducing their own transfer file solutions. This including Apple AirDrop, Huawei Share, Mobile Direct Fast Exchange, as well as the Google and Samsung's Quick Share. So this trend highlights the importance of improving the user experience by enabling seamless content sharing between different devices. And to our knowledge, all of the above products are using the peer-to-peer Wi-Fi technology to transfer data. So in this talk, we focus on the performance of Wi-Fi Direct, and we believe our study also applies to other Wi-Fi based peer-to-peer technologies, such as the proprietary Apple Direct Link protocol. So to begin with, we conduct a TCP speed test in an office room, so where there are tens of other devices that might cause interference. So we have optimized the TCP by setting a large socket size buffer and enable the window scaling. So the table compares different Wi-Fi standards and their respective performance. So we can see in the result, only half of the physical rate is utilized. For example, we take the Wi-Fi 6, for example, which can support up to 1.2 gigabit per second, but only achieves 600 megabit per second. So we asked the question, why is there a huge gap between the physical rate and the throughput? So we take today's most popular Wi-Fi 5 standard as an example, which also known as the 802.AC. So such devices typically equipped with two antennas. That means it has a maximum physical rate of 866 megabit per second. And if we use a perf tool such as iPerf to test the performance by ensuring the network interface never runs out of packets, we can get the maximum practical line rate of about 700 megabit per second. And we define this rate as wireless line rate. However, when it comes to the real-world data transmission over TCP connection, even with careful parameter tuning, the maximum achievable throughput is much lower at about 450 megabit per second. And that's only half of the physical rate. So we can see in the figure, there are two huge gaps. And the first gap is caused by the protocol overhead, retransmission at MAC layer, and some collision avoidance mechanisms. Such overheads are unavoidable in a real-world environment because all the devices share the same medium, wireless medium, and we cannot eliminate the noises and interference. And for the second gap, we argue that it is due to the design of the transport protocol. So specifically, we attribute the reason to 3 key factors. First, the hacking policy used by the transport protocol like TCP or QUIC exacerbate the channel contention. Both the data packet and the acknowledgement packet share the same medium, so that it leads to an increased interference. And second, the widespread use of congestion control, which is tailored for the internet scale connection or data center network, they require probing or estimation of the network states. However, this process often results in an unnecessary startup phase or overreaction to the packet loss and decrease the throughput. And finally, the existing flow control only consider the transport layer buffers, and it ignores buffers at other layers. So they use a fixed window size, which can cause packet loss at other queues or buffers. Therefore, all of the above factors result in the link underutilization. And the most recent work published in SIGCOMM 20 tries to address the problem caused by frequent acknowledgement. And in this talk, our goal is to push the limit of the achievable throughput. And our design removed the congestion control and used intelligent flow control to approximate the practical line rate of the wireless bandwidth. Note that there's still a small gap because unlike speed tests, we need to provide other features like reliable delivery. So we present SMUFF, a reliable file transfer service designed with two design goals. First, it aims to achieve the wireless line rate of the Wi-Fi direct connection, ensuring efficient use of the available bandwidth. Second, we seek to design SMUFF to provide reliable delivery and require low system resource usage. So in designing SMUFF, our key insight is that we can monitor all the on-path buffers. So for comparison, in an internet or data center connection to manage the buffers or queue inside the network, we use congestion control or the in-band network telemetrics to monitor the buffers or queues inside the network. And in contrast, in direct transmission, there are no intermediate nodes such as the router or switches. So therefore, we can monitor the state of each buffer throughout for the whole packet life cycle. And here is an end-to-end pipeline of a file transfer task on a typical Android device. So the data is read from the sender's disk and passes through various buffers and finally arrive at the receiver disk. And during this process, each buffer is observable by the sender. The receiver can report the buffer state with a feedback signal within an RTT. So among this buffer, we have identified 3 buffers that can cause overflow or underflow without proper flow control. And we left the analysis to the paper, and here we focus on how to manage this on-device buffers so that we can achieve the line rate. We model the transport data path as a series of connected buffers and consider the traffic as a flow that sequentially goes through each buffer. And our key idea is to maintain an appropriate amount of data in the bottleneck buffer. Since the overall throughput is determined by the bottleneck, we can get the maximum throughput as long as the bottleneck buffers have data to send. So the problem is how much data we need to keep in the bottleneck buffer. For simplicity, let's consider one single buffer. So we denote the incure rate and decure rate as V in and V out respectively. And the amount of data in the buffer using an uppercase X. So if there are 2 less data in the buffer can go empty and result in underflow and link underutilization. The buffer can go empty because of the increase of the decure rate or the decrease of the incure rate. So there is a control delay between the sender and the receiver, and therefore we need to backlog enough data in the buffer to ensure it won't go empty. And this amount of data can be denoted by such expression. Here, V out upper means the upper bound of the decure rate, and in our case, it's the physical rate. And V in lower is the lower bound of the incure rate, and is 0 in this case. And in our implementation, we try to reduce the memory usage, so we use another method to set the lower bound and upper bound, and that detail is left to the paper. And one thing to note that is the control delay can be large. Although our connection is only one single hop, there is a non-negligible control delay in the buffer management. So as illustrated in the figure, the x-axis is the TCP sending rate, which is controlled by the application. And the y-axis is the RTT read from the kernel data structure. So as we can see, although there are no router in our setting, the round trip time can still increase up to 25 milliseconds. The reason is that the on-device buffer bloat, so such as the Wi-Fi data frame batching, increases the RTT. So therefore, the sender cannot get the buffer information in time. That is why we need to backlog data in the buffer to handle the link underutilization. So, and similarly, it is also necessary to allocate sufficient buffer room to handle the incoming data. And we can also calculate another threshold. So these two requirements actually conflict with each other, and this conflict leads us to define a safe range for the amount of buffer data. And this range ensures, even in a situation where the state information is infrequently updated or out of date due to the limited feedback from the receiver, the buffer is still remain protected from the underflow and overflow. We can also generalize our idea to more buffers, and the sender collects the buffer state from each buffer and update its sending rate. Now we introduce how we set the sending rate to achieve the above goal. So again, our goal is to maintain an appropriate amount of data in the bottleneck buffers. So we need to enumerate each buffer to identify the bottleneck buffers and calculate a target length within the safe range. We next calculate the incure rate so that to maintain the queue length in the safe range. To calculate the incure rate, the sender needs to collect metrics from the receivers, which include the buffer occupancy, the decure rate, as well as the control latency. So SMUFF also have other optimization to make it practical to deploy. It reduces the frequency of the ACK and use negative ACK and selective ACK to speed up the loss recovery. And it also uses packet aggregation to reduce the CPU usage, and we found the batching is actually an effective way to reduce the system overhead. And we also try to reduce the impact on other flows with flow prioritization. And that detail can be found in the paper. So SMUFF is implemented as a system service, so the application can use the API to deliver the file to its peer. And it only uses standard system API to get the buffer state, and we have successfully deployed it on 4 different form models. And finally, we evaluate the performance of SMUFF for different scenarios in our realistic environment. So in all cases, SMUFF outperforms other transport schemes, and it improved the performance by around 18% compared with the state-of-the-art solutions. So moreover, SMUFF reduces the flow completion time, and the improvement is significant for small file because it bypasses the slow start process. And it also works with different Wi-Fi standards and achieve an average link utilization of 89% on Wi-Fi 5 and 91% on Wi-Fi 6. So here are the takeaways from this talk. So in summary, we propose a file transfer service called SMUFF, and it can achieve up to 94% of the practical line rate. And we show that transport schemes tailored for the internet often fail to fully exploit the link utilization. So we propose SMUFF. And we also know that SMUFF require a large buffer, which is a limitation of our work. And as AR and VR application is becoming more and more popular, and SMUFF is not designed to achieve a low latency. So we envision the future work can make some trade-off between the throughput and latency. And that's the end of this talk, and thank you. I'm happy to answer any question.